Hello, everyone. This is Keith from eBay DSS team. It's my great pleasure to be here to do the presentation in the pitfalls and the best practices we learned during the migration from analytic DBMS to Apache Spark. About us, we are from eBay Data Services and the Solution team, and focus on big data development and optimization, also the data services part. Now we have more time on the migration from ADBMS to Spark. Talks from our team about the migration, but with different content, and presented on the Spark Summit 2018. Okay, here is the agenda of the talk. First, we will go through some background, some background information, and then we will go into the use cases and the best practices. Finally, we will talk about the auto migration framework. When we migrated to Spark, I think it's clear now. We are all impressed by the power and advantages of Spark. It's open sourced. It's unified processing engine for streaming data and the batch data. Also, it supports machine learning use cases and AI use cases. Now, Spark is the unified processing engine to support our EDW use cases. Our current Spark cluster environment, we are using the Spark version 2.1, and now we are upgrading the version to 2.3. Okay, let's go into the use cases and the best practices. Before we go to the detail, let us take a look at the key steps for typical migration from ADBMS to Spark. First, the table schema or DDL has to be translated to Spark version. It may not be a simple one-to-one mapping. Then we do the SQL conversion. After that, the historical data could be need to be copied from ADBMS to Apache Spark. Then, this is ready to submit the Spark SQL job to the Yarn cluster, and we use Yarn for the resource management. When the SQL finished, a post-data quality check will be a must to ensure the data quality. Besides that, performance tracking and logging for error passing and the performance improvement is also necessary. In this talk, we will focus on the first two parts, that is the table schema translation and the SQL conversion. Okay, for the table schema translation part, I will show three cases. The first one is single partition table is not enough. It means that suppose there is a table X on the ADBMS, and if we create a single partition table in Spark SQL for daily population purpose, no matter we use different partition or create view on different partition and you may see this error, cannot overwrite a path that is also being read from. This is because Spark will first delete the destination directory before insert or write. Well, have only delete or move in the final stage. Why? This is because this is mainly for performance purpose. You can check the Jira for more detail. So instead, we have to create two tables. One is table X, one is table X underscore merge. And here is the sample. Table X underscore merge is a partition table and keeps snapshots for each day. And the table X only point to the latest partition for the downstream reference, and also used for populate last snapshot. The usage of these two tables will be shown in the following SQL conversion part. With this trick, before error could be bypassed. The second case is the column name is case sensitive. In DBMS, column name is usually case insensitive, when do the data selection. Well, this is not true on Spark, especially when the file is stored in the file format like Parquet, which store the schema along with the data. So we suggest to use lowercase for table schema to avoid this, such issues caused by the different column name case sensitivity. Otherwise, you may see error if the table DDL say use uppercase. Well, you try to select data with a lowercase column name. The worst case is that it may return wrong result and cause data issue. For example, in Spark 2.1, it will throw error if we create table with a column with an ID column in uppercase and store in Parquet format. Then we do selection with a lowercase ID column and has a filter on that. Well, on Spark 2.3, it will return unexpected empty results silently. We have reported this issue to the community to align the behavior, and this issue has been fixed in 2.4. The third case is actually a type regarding the column type mapping between ADBMS and Spark. Before version 2.4, filter on decimal typed integer could not be pushed down to Parquet, but it works with pure integer or long type. So it's better to map the decimal type integer to the pure integer or long type for better performance. Let me show you a sample. Here is a table with two columns. One is a decimal type integer, ID1, and the other one is the pure integer, ID2. As you say, the filter on the ID1 is actually not pushed down, so there would be a full table scan. Well, filter on ID2 could be pushed down, and it could save time in most cases. To enhance this useful filter pushdown feature in Spark for Parquet format, we submitted a few JIRAs and pull requests, like support date type, decimal type, etc. Those features are available in 2.4 now. Okay, after the table schema translation is finished, now let us go to the SQL conversion part. I will show 5 cases for this topic. The first case is the conversion of update-delete query. As we know, Spark SQL does not support update does not support the update or delete yet now. The update or delete query has to be translated to an insert or insert overwrite. The transformation should be semantic equivalent. That is to say, it should get the same output data set. Okay, here is a typical use case of daily data merge. The daily data or incremental data part is pulled from OLTP system and then merged to a target table in ADBMS with an update and insert operation. In Spark SQL, it could be converted to a full outer join or union all to get the same result. Here, table X references the yesterday full data and populate a new snapshot in table X underscore merge. The second case is insert. Insert conversion looks straightforward, but actually not. ADBMS will implicitly remove duplicate rows for set tables, which is kind of like the set collection in Java. In that case, a group by or distinct has to be added to the insert query. Okay, here is a ADBMS use case, and you can see that the target table is defined as state table. So in Spark SQL, we will add a distinct to get the same result. Actually, for this issue, at first place, we did not notice this. until we did the post data quality check and found the difference. The third case is the number expression conversion. It is not that easy also. For example, the rounding behavior. ADBMS and Spark use different rounding rule. It behaves differently when the value after the last number to be kept is just half of 5. For ADBMS, it uses a half-even rule by default, which means it will try to make the last digit to be kept as an even number. If the last digit to be kept is an odd number now, then it will be increased by 1 and become an even number. If it's an even number already, it will be kept as is. Well, for Spark, it uses a half-up rule by default, which means it will always add 1 to the last digit to be kept. Here is the sample on the ADBMS. As you say, 2.5 would be rounded as 2 since 2 is already an even number. Well, 3.5 is rounded as 4 since 3 is an odd number. For Spark, to get the same result, we can use the bround function. Okay, here in Spark, we use bround and get the same result and ADBMS. The second difference is the number division result. ADBMS return an integer for integer division, while Spark always return double. It may cause data description as well. For example, the division result is used in a case 1 expression and return different value for different integer result. To overcome this difference, we could explicit cast the division result to integer in Spark SQL. Here is the number division sample. And we can see that 3 divided by 4 returns 0 on the ADBMS, and on Spark, it returns 0.75. So in this case, we have to add an explicit cast like this to get the same result as ADBMS. The fourth case is the string expression conversion, which is more tricky and headache. The first one is the case sensitivity in comparison or group by. ADBMS is case insensitive in comparison, while it is not true in Spark SQL. To bridge the gap and get similar result, we have to apply a lower or upper function to string column before comparison or group by. For example, as you say, the table A and table B both have column 1 and contain the value ABC in different cases. It still returns result when joined on column 1 since it is case insensitive. Spark would return empty result if directly joined on column 1. Applying lower or upper function to both sides to get the same result as ADBMS. The second pitfall in string expression is due to the auto trim trailing space feature in ADBMS. This looks reasonable for fixed length chart type, as space would be padded if the actual data length is less than the predefined data length. So ADBMS would apply an auto trim before comparison. Well, there is no such thing in Spark. In this case, a trim function has to be applied to such chart type column in Spark SQL. Here is a sample. Column 1 in table A has value ABC, but red padded with spaces. It still return result when joined on column 1 on ADBMS. And this is the Spark SQL sample. As you can see that Spark SQL actually return empty before a trim function is applied to the column 1 in table A. Besides above cases, actually there are many other cases leading to data difference between the two systems, even though run the same query on the same data site, like the character encoding issue, string locale, decimal or double precision issue, and so on. The fifth part in SQL conversion is the special query type to handle the recursive query. Spark SQL does not support the recursive query yet at this moment. Well, we can make it with the Spark Dataframe API. Recursive query is actually a create table expression, or CTE. A recursive query basically composed of two parts to generate the final result: an anchor query part and an iteration query part. The red picture is a logical execution data flow. A typical use case for recursive query is the employee manager problem. Given a table with employee ID and its direct manager ID, try to find out all the managers, either direct or indirect, of an employee. In this case, first, we would get the initial data set from the anchor query, the employee table. And then initial data set would be used in the iteration part of a recursive query to get the upper two level managers of an employee. And then this data set would be used again in the iteration part again to get the upper three level managers of an employee. This iteration would continue until there's no new employee manager relation, or it has reached the hard iteration count limit. The implementation of recursive query with Dataframe API is basically the same as a logical data flow. Well, there are two key design tips for our use cases to make it scalable and could handle more than 8,000 iterations with an acceptable performance. The first one is to pre-sort and bucket the reuse table in the recursive query part if possible. This is to avoid shuffle and sort in each iteration. The second one is to write out the data frame or RDD in each iteration. It may look unreasonable at first place. Why not use the RDD cache? Well, the RDD cache would cause OOM in stack size due to the too deep RDD relation when we do the RDD serialization or deserialization in the driver side, as RDD is actually not a data site, but just store the dependencies. Here is a query explain and performance figure. Spark uses 8 hours and ADBMS uses 6 hours. Spark could be further improved in the new version, I think. Okay, after showing the pitfalls and the best practice, it looks like a correct end-to-end manual conversion would seem really error-prone and time-consuming. Also, it's boring to repeat such process for each table. Joy principle tells us we should avoid repeat, and we need automation. Yeah, we did that and developed the automation tool to accelerate the migration. Let us go to the third part of this talk, the automation deep dive. Let us say the automation scope. We have 5,000 target tables, which are identified as candidates for auto migration. Manual migration of 5,000 target tables cost is too high. It usually needs 3 dev days for each table in average, according to our experience. That's why we developed the auto migration framework. The auto migration workflow is basically the same as manual migration, but the auto migration strategy is different. For many migration, domain owners could do the migration case by case and prioritize the tables based on their own need. For auto migration, to reduce the complexity, the tables would be migrated in a bottom-up way, which means the similar target tables, which usually is direct pull from OLTP system, go first, and then the dependent higher level tables, which are populated by a few above simple tables, go second, and then the other higher level tables can start if all its upstream table already on Spark. I would briefly introduce the automation framework. If interested, you can take a look at our before presentation on this. We get the table information from metadata component. Also, there is a DDL generator for creating tables, SQL Converter for automatic ADBMS SQL conversion to Spark SQL, data mover for one-time data copy, and some other components like release assistant, data quality check, and log parser. The whole architecture is metadata-driven, service-oriented, built on top of Spring Boot, so that the components or services could be composed and called individually. For auto migration, the whole process is controlled by the controller process. For some services like data mover or SQL converter exposed to the end user, they can directly call the service with necessary input. In this talk, I will talk about the three common components here: the metadata component, DDL generator, and the SQL converter. Metadata is essential, and the information is collected from existing ADBMS system by passing the query logs, and also from the existing daily pipeline info. It includes the table schema info like column type, default value, the table population query list, and its running sequence. Also, the upstream table list. With this information, we can actually build a data lineage. The whole metadata info is stored in Neo4j, and the table population relationship decide which table could be migrated first. We call the table without any upstream target table as direct pull tables, which means they are directly pulled from OLTP system to ADBMS without any transformation process. They are the base tables. After the base tables are ready on Spark, the migration of upper level tables, which is populated with those direct pull tables, could be started now. The process continues, and finally, all the tables could be migrated to Spark. In this picture, we can clearly see the table lineage info. DDL generator. There are three main goals in DDL generator. The first one is to map ADBMS table to Spark table. It's usually not a single. It's usually not a simple one-to-one mapping. As we said before, table X in ADBMS would be mapped to table X, and table X and Spark merge in Spark. The second goal is to map ADBMS data types to Spark types according to the best practices, like map decimal type integer to the pure integer or long in Spark. The third goal is to define file input format for state tables, which are the intermediate tables whose data is loaded from file extracted from OLTP systems. The input files format could be CSV or some ETL2's specific file format. New input format has to be developed to let Spark read the files correctly. Here is the table model mapping between ADBMS and Spark we have already known. And here is two samples for the state tables. One is CSV, and the other one is a customized input format to read the ETL2 specific files. Then let us see the SQL conversion part. To do the SQL conversion, first we need to identify the existing ADBMS SQL statement. We use enter to pass the ADBMS query to the abstract syntax tree. And then we walk through the tree and apply the conversion rules. Finally, the Spark query is generated according to the output of the rule engine. Enter is a language parser generator based on the grammar file. It can then pass the input string and compose a syntax tree for later walking through. And this is a DDL grammar in enter format. And this is a general query grammar. We manually write the grammar for the ADBMS SQL as it is a closed product. The rule engine. The rule engine is a rule-based processing. It will identify SQL query pattern first, and then do conversion based on conversion rules. For example, for the single update and the insert case, it would be converted to a full join, as we said before. For multiple update delete case, it will store intermediate step result into temp view and then do final single merge. It would identify default values in ADBMS table and then fill in the Spark SQL. Also convert the ADBMS functions to Spark version based on the mapping. The last thing is to bridge the gap. For the cases like we mentioned before, the case sensitivity issue and the auto trim in string issue. Here is one real use case. Delete and insert would be converted to a union all. Update or insert or merge could be converted to a full join or union all as well. Multiple update and insert case would be handled as with temporary view. That is to say, we will create temporary views to hold the intermediate results and then do a final merge. The last section is the be part of the community. We have contributed more than 100 JIRAs and pull requests to the Apache Spark community, and most of them have been fixed or merged to the master branch. Also, we are still actively working with the community to improve Spark. Okay, we have pretty much for this talk. Time for the question. Thanks.